A massive steel giant, weighing hundreds of tons, towers hundreds of feet in the air, its arm extending over a busy street. Every instinct says it should topple. So why doesn't it? The answer isn't just one thing. It's a chain of masterful engineering. We're going to reveal the incredible strength of its steel and uncover the hidden foundation locking it to the earth. We'll show you the balancing act that defies gravity, explain why its controlled sway is a feature, not a flaw, and explore the fail-safe systems that prevent the unthinkable. The truth is far more impressive than you might think. Before a tower crane even starts its climb, its fate is decided deep in the ground. The most critical component ensuring a crane's stability is one you will never see: its foundation. For most tower cranes, this begins with a massive reinforced concrete pad. We're not talking about a sidewalk slab. A typical foundation can be 30 feet by 30 feet wide and over 4 feet thick, consuming around 135 cubic yards of high-strength concrete. This slab, weighing over 540,000 pounds, acts as a colossal paperweight, creating an immense moment of resistance against the overturning force of the crane. This concrete cures for weeks, tested and retested until it reaches a compressive strength often exceeding 4,000 pounds per square inch. Embedded deep within this concrete is the starter section, or grillage, the first piece of the crane's mast, securely bolted into the foundation. It becomes one with the earth. But what happens when you're building on solid bedrock just a few feet below the surface? Pouring a massive pad is inefficient. In these cases, engineers drill directly into the rock, embedding long steel anchors dozens of feet down. These anchors are then grounded in place and tensioned, essentially bolting the crane's base to the very bedrock of the city. The crane's stability is no longer reliant on a massive weight, but on the immense sheer strength of the planet itself. This foundation is the unsung hero of every skyscraper build, a multi-$100,000 investment buried before the real work even begins. It's a testament to the old industry wisdom. You can't build high without first digging deep. But this subterranean anchor is only half the story. It prevents the crane from tipping over at its base, but what stops it from snapping in the middle? The real genius of a tower crane isn't in resisting forces, but in balancing and absorbing them. The most visible part of this is the counterweight. Look at any crane and you'll see the long horizontal jib, the working arm, and a shorter, thicker arm pointing in the opposite direction. This is the counter jib, and on it sits the crane's secret weapon: up to 20 metric tons of precisely engineered concrete blocks for larger cranes. They are calculated to perfectly balance the weight of the jib, so the crane is in a state of near-perfect equilibrium. It's a simple seesaw on a monumental scale. But this balancing act relies entirely on the integrity of the mast. Now, not all steel is created equal. By adding different elements like carbon and manganese, metallurgists can create alloys with vastly different properties. The most important property here is yield strength, the amount of force a material can take before it permanently deforms. For a tower crane mast, engineers specify a high-tensile, low-alloy structural steel, a material engineered for extreme strength without adding excessive weight. It's easy to overlook just how strong this specialized steel is. We see it everywhere, so we take it for granted. Let's put it in perspective. This type of steel has a yield strength often ranging from 50,000 to 70,000 pounds per square inch. What does that actually mean? It means a solid bar of this steel, about an inch thick, could suspend the weight of 10 Ford F-150 pickup trucks before it even begins to permanently deform. It is an almost unbelievable concentration of material strength. Now, that strength is multiplied by the geometry of the lattice mast. This design isn't for looks, it's a masterclass in efficiency, using interconnected triangles to distribute forces. This creates a structure that is immensely strong and rigid, yet far lighter than a solid steel column would be. However, Perfect rigidity can be a fatal flaw. A structure that is too stiff is brittle. If you put a massive sudden force on it, like a powerful gust of wind, it has no choice but to break. This is why cranes are engineered to sway. That movement you see isn't a sign of weakness, it is a critical design feature. The steel mast is designed to be elastic, to flex and bend under load. Much like a tall tree in a storm or a fishing rod bent under the strain of a big catch, the sway allows the crane to absorb the kinetic energy of the wind and dissipate it safely along the entire height of the structure. If it were perfectly rigid, that same gust of wind would concentrate all its force on a single point, risking a catastrophic fracture. The controlled sway is a safety valve, turning a violent punch of wind into a gentle push. To aid this, when the workday is over, cranes are put into weather vane mode. The slewing brake is released, allowing the top of the crane to rotate freely and align with the wind. This presents the slimmest possible profile, drastically reducing wind load. So when you see a crane turning on a windy night, it's using an ancient principle to protect itself. But even this combination of balance, strength, and elasticity has its limits. There is a point where the crane simply becomes too tall to support itself. A typical tower crane can stand on its foundation unsupported, what's known as its freestanding height, up to about 265 feet. Beyond this point, the bending moment at the base of the mast, caused by wind and the crane's own weight, becomes too great. The crane would risk buckling like a soda straw. So, how do we build towers that are thousands of feet tall? The solution is simple. When the crane gets too high, you attach it to the very building it's constructing. This process is called tying in. As the building's superstructure rises, engineers install horizontal steel support collars, or ties, that connect the crane's mast to the building's structural frame, usually its concrete core or steel columns. These ties are not just simple props, they are robust, engineered frames that effectively turn the building itself into a massive brace for the crane. Once a tie-in is installed, it transfers most of the lateral wind load from the crane's mast directly into the building structure. The building is designed to handle immense wind loads anyway, so it can easily absorb the extra force from the crane. With its lateral stability now secured by the building, the crane can climb higher, adding more mast sections. The process is repeated every 80 to 100 feet. The crane essentially hitches a ride up the side of the building it's creating. This symbiotic relationship between crane and structure is what has unlocked the modern age of the super tall skyscraper. From the Burj Khalifa in Dubai to the new towers rising in New York, none would be possible without this straightforward but critical technique. It's a global symbol of ambition, a steel umbilical cord connecting the machine to its creation, allowing both to reach impossible heights. But with hundreds of feet of steel and tons of load in the air, what happens when things go wrong? Despite the incredible engineering, a tower crane is still a machine operating at the limits of physics, and the potential for failure is always present. This is where a suite of non-negotiable safety systems comes into play. The electronic guardians that protect against both mechanical failure and human error. The most important of these is the load moment indicator, or LMI. This is the crane's brain. It uses sensors to constantly monitor the angle of the jib, the weight of the load, and the radius at which the load is being lifted. It continuously calculates the overturning moment and compares it to the crane's pre-programmed load chart. If the operator tries to lift a load that is too heavy, or move a load too far out along the jib, the LMI doesn't just sound an alarm. It can lock out the controls, preventing the dangerous action. It's an electronic backstop that makes exceeding the crane's structural limits nearly impossible. Working alongside the LMI are other critical sensors. Anemometers measure wind speed in real time. If gusts exceed a preset limit, typically around 45 miles per hour, operations are halted. Limit switches on the trolley and hoist prevent the block from being pulled into the jib or the trolley from running off the end. Every critical function has a failsafe. This creates an environment of controlled risk. There is an inherent tension in the industry, a deep respect for the power of these machines, and the consequences of complacency. But that tension is met with the hope that comes from innovation. These automated systems are not a replacement for a skilled operator, but a partner, providing a layer of protection that allows them to work efficiently without crossing the fine line into danger. Next time you see a tower crane swaying against the skyline, know it's not about to fall. It's built to flex, a precision machine that dances with the wind while lifting tons. From its hidden concrete base to the high-tech controls in the cab, every part is a link in a chain of engineering genius. Building the future takes more than steel. It demands balance, precision, and respect for nature's forces. Thanks for watching Hard Hat Industries, your source for serious machines doing real work. If you like this, hit like, subscribe, and turn on notifications so you don't miss what's next. Until then, keep your head down and your gear running.